Hello and welcome to Team VLSI. Today in this session we are going to discuss setup and hold time equations in the fridge of STA concepts, and I think there are many of literature available on this topic, but problem is that many places you will not able to understand completely these equations. So I will try to simplify these things with examples, and I will keep the things very simple in this session. So let's begin. Please like this video and subscribe our channel. Our channel is youtube.com/teamvlsi, or you can search Team VLSI on Google. So first of all, what are the possible scenarios for the analysis? A typical register to register path is represented like this, where there are two flops. One flop launches the data and other flop captures the data. The flop which launches the data, here FF1, is called launch element or launch flop, and the flop which capture the data is called capture element or capture flop. And all these things is synced with the clock signal, edge of the clock signal in case of flip-flops. But this is not the limitations. In place of flip-flops there could be a latch also. So we need to extend this analysis for latch also. So I have planned to discuss all the things in this way. In case 1 we will discuss the analysis for the where both the launch and capture elements are flip-flops. In case 2, launch element is flip-flop and capture element is a latch. There could be a different case, like where launch element is a latch and capture element is a flip-flop, and case 4 could be where both the elements launch and capture could be latch. Okay, and when we talk about the flip-flop or latch, again we have two types are there. In flip-flops there could be a positive edge triggered flip-flop and a negative edge triggered flip-flop. Similarly, in latch there could be a positive level sensitive latch or negative level sensitive latch. So we have sub cases where we will discuss combination of positive and negative flip-flop for latches in each cases. So this video could be lengthy, so I will break this video in many parts, but I will make all the things clear. So first of all, let's discuss the case 1 where launch and capture both elements are flip-flops. You can see here, and specifically both are positive edge triggered flip-flops, which is more common case in the ASIC design. First we will discuss this and move to the next scenario. Let's see the derivation of setup timing equation. So setup analysis, you can see here there are two flip-flops, and between that there is a combinational path, lots of combinational logic is sitting here, and both the flops is operated by a single clock, and clock is and clock signal is propagated from the clock pins to the both the flops. This is the typical scenario of edge to edge path analysis, right? Here launch and capture both are flip-flops and both are positive edge triggered, as we decided. Okay, so you can see typical a clock signal is like this, and it's we suppose this positive edge of clock will come to this CK pin of flip-flop 1, and it will launch a data and take a time theta to reach. After reaching the clock signal to this point, and it will take time theta to reach the data to D pin of the flip-flop 2. Obvious data will be moved from the D pin of flip-flop 1 to the D pin of flip-flop 2, but it will take further a time clock to Q delay in this part, and it will take a time combinational delay in this part, right? And it will be captured by the flip flop 2 when next edge of clock comes to this flip flop, I mean flip flop 2. And the time difference between these two rising edge of clock is our clock period of the clock, right? So we will indicate it by T of clock, that is time period of the clock signal. Okay. So mathematically we can say that as per the definition of setup timing, our this data should be reached sometime before the arrival of this clock edge. So, and this clock edge will appear after TCLK time. So we can say that theta should be less than T of clock, right? And as I have told, this theta has two parts. One is clock to Q delay and second is combinational delay from Q to DP here. So we can rewrite this this terms as TCQ plus T combo should be less than T of clock, right? So let's add more practical scenario in this situation. So actually what happens, clock is not suddenly appear at this CK pin. It will take some time to propagate the clock signal from clock pin to the CK pin of the flop, and that is called latency. Suppose flip flop 1 has latency L1, then you can see here its rising edge will appear after L1 time. After L1 time, when the clock edge appear at the clock pin, right? And we can visualize that here. Ideally, at these points, the clock edge should appear on both the flops, but due to latency, the rising edge will appear at flip flop 1 after L1 time, right? And after appearing this rising edge, it will launch the data. Okay, and similarly for flip flop 2, it will receive the rising edge after L2 time from the rising edge at the clock pin. So it has latency L2. So again, instead of receiving the rising edge at this point, it will be delayed by L2. And after and on this point data will be captured, right? So let's include this latency in our equation. So what will happen, in left hand side you can see that now delay the time to reach the data at D pin of flip flop is not only TCQ plus T combo, but also this much of delay, because first clock will propagate from clock pin to the CK pin of this flip flop, then it will take TCQ clock to Q delay, then it will take combinational delay. So all the three parts will be in left hand side, and instead of appearing the clock at after TCLK, it will take further L2 latency to capture the data. So right hand side L2 will be added, right? Now add one more scenario, real time scenario, that is clock uncertainty. So instead of we have discussed the clock uncertainty in the previous video. I will provide the link of that video in the description, and you can go that video through the I button here. So what clock uncertainty says that instead of appearing this clock edge sharp at this point, it could be uncertain for us some duration. So if it appears late, that is no issue for the setup analysis, because we want actually we want this data should reach before, and this should come later. So if it moved the if it becomes late, then no problem, but if it becomes early, then it is problematic, and we should take care of that case. So we need to subtract this much of time on the right hand side to consider this setup uncertainty, and our final equation will be look like this: L1 plus TCQ plus T combo should be less than T of clock plus L2 latency minus setup uncertainty. We have one more important practical factors, that is setup time of flip-flop 2, and it says that data should reach on appearing the clock before the setup time. That is the basic definition of the setup time. So let's include this factor in our equation. So what will become, again TF factor will be subtracted on the right hand side. So our final equation will look like this: L1 latency plus TCQ plus combinational delay should be less than clock period plus latency of the flip-flop 2 minus setup uncertainty minus setup time. Okay. So left hand part should be lesser than right hand part, and the left hand part is actually the time to travel the data. So that is called data arrival time, or sometimes it is denoted by AT, and right hand side is called data required time, or RAT. And you can see here RAT is this much of time, and the difference between data required time and data arrival time is actually called slack. So you can see right hand RAT should be greater than AT. That's why RAT minus AT is your slack, and we want a positive slack in order to meet the setup timing. But we are not fortunate enough that every time we will see the positive flag. Mostly we fight with the negative flag always. So a negative flag means setup violations, and if there is a setup violation, we need to fix it. Okay. So one more thing, L2 minus L1, that is the latency of the flip-flop 2, and the differences between the latency of these two flops is called skew. Let's more simplify this equation. So we can what we can do that we can subtract the L1 in L2 on the right hand side, and instead of L2 minus L1 we can write T skew, right? So our simplified equation becomes T clock to Q, delay of clock to Q plus combinational delay should be less than clock period plus skew minus setup uncertainty minus setup time. Hope I have explained this in easy way and you have understood. If not, kindly revise once more the derivation. It will be clear to you. And take away point from this is our setup analysis is always done between the next by default it's next clock. Sometimes we provide the multi-cycle, so to one cycle, after one cycle setup timing is being checked, right? So next we will see an example. So here we have given that clock period is 1 nanosecond, combinational delay is 650 picosecond, clock to Q delay is 120 picosecond, and each clock buffer's delay is 20 picosecond. Setup timing, setup uncertainty of this clock is 180 picosecond, and setup timing of the flip-flop 2 is 150 picosecond. So let's analyze first, is it meeting the setup requirement or not. So we have seen the general equation of the setup analysis is like this. So put all these value here. So L1 will be means latency of this flip-flop, that is delay of two buffers here. We have ignored the interconnect delay, so it's fine here. So it will be 40 ps plus clock to Q delay is given 120 ps plus this combinational delay is given 650 ps, right? So arrival time will be this much, and required time what will be? First clock period, that is 1000 ps, since 1 ns is equal to 1000 ps, and AT is the L2. L2 is 4 buffers here, so 20 into 4 80 ps will be the latency. Minus setup uncertainty is given 180 ps, and setup timing is 150 ps for right hand side. So RAT will be 750 ps and arrival time will be 810 ps. For what would be the slack? What I have told for slack is in setup analysis required arrival time minus arrival time, and that comes here minus 60 ps. What negative sign indicates? A negative sign indicates here it is a setup violations. Okay, that's the very obvious scene for us. We are not fortunate enough that we will see the positive slacks always. So if there is a set of violations, then definitely there is a way to fix it. I am not going to discuss the way of fixing in much details here, but I will provide just a hint how can we fix it. So let's see the way of fixing set of violations. So what are the scopes to fix that? So I will divide various paths where we can fix that. So first of all, let's discuss this data path where all combinational cells is sitting, and say it's path 1. So in path 1, what can we do? Path 1's delay is what? T combo, and T combo is where in this equation is left hand side, and left hand side should be lesser. In order to fix that, it should be left hand side should be lesser than the right hand side. Okay, so definitely if we reduce the T combo, then it will meet the requirement, right? So from here we can say that we need to reduce the delay in the combinational logic path. So how can we do that? So path 1, we need to reduce this delay, and option is VT swap. What is actually VT swap? So there are various VT cells in our design, and according to the VT, our VT here means threshold voltage. According to the threshold voltage of the cell, its delay vary. Higher the VT, higher the delay. So what we want, we prefer here lower delay cells. So we will change the higher VT cells to the lower VT cells here, and in this way, if we can manage 60 ps of timing, means if initially it is 650 ps, and we can by converting the HVT to LVT, if we can manage it to 590 ps, then our problem is solved, right? Second thing, you can see here till this point clock is common for both the launch and capture flop, and that's why this point is called common clock point. And consider this path. Will this path impact if we change the delay of this path, or increase or decrease? Will it impact? Obvious not, because whatever delay we will add here, it will equally contribute in L1 and L2, and L1 and L2 is appearing both the sides, so definitely it will cancel out. So path 2 has no effect in the setup fixing. Next, move to the this path. What will be the impact of this path? So if we increase the delay of this path, definitely it will increase the L1 only, not L2. so L1 will going to increase. If L1 is going to increase, it will worsen the case. So definitely we need to decrease the latency L1. So we need to decrease the delay in this path. So path 3, decrease the delay, and decreasing the latency of the flip flop 1, that is the launch flop, is called early clocking. Okay, next scope of fixing is in this path. So where this delay appear in the equation? This delay is contributed in L2, and L2 in the right hand side, and right hand side part should be greater than the left hand. So definitely if we increase this delay, will help to fix the setup. In path 4, increase the delay. Our fixing way could be increase this delay. If we do this propagation delay more delayed, means this is called actually late clocking. So it will help. And here we can see that 20 ps is 1 clock buffers delay. So if we add 3 clock buffers in this path, definitely it will solve our problem and fix the setup timing. But be very careful while doing the early and late clocking. So you cannot do blindly the early or late clocking. You have to analyze the previous path and the next path. Suppose in order to meet the setup timing in this path, you are doing this clocking is late, means late clocking of the capture flop. Definitely by adding 3 more buffers, it will solve our problem here. But what will be consequences for the next path? So actually this capture flop will be a launch flop for the next flops, and if we are doing late of this late clocking of this flop, it might violate the setup timing of the next path, because what we are doing increase in the latency of the launch flop for this path, the path next to this consideration, right? And similarly effect will be for the previous path if we play with this timing, right? So our always priority is that we should first play with the data path only. If it is fixed by data path, changing in the data path means BT swapping in the data path, then it's good and well. If not, then we will play with the clock path. But while doing the clock path, we must analyze the previous paths and the next path, right? From here we can see that if this path and this clock is make early, it will help. So for the launch flop we can do the early clocking on and for the capture flop we can do a late clocking, but always be attentive while doing this and analyze the previous and next path, right? So next let's see the derivation for the hold equations. So we have seen this type of range to range path in the previous slides, and suppose the same TC CLK, that is period of the clock period, then when clock reaches at this point, it will launch the data and will be received by this clock. And as per the hold time requirement, it says that it should not be your data path should not be fast enough that it should reach before the hold time of this flop. And mathematically we can write that theta should be greater than t hold, right? And we can divide this path into two parts, one is clock to Q delay and one is combinational delay. So we can write that TCQ plus T combo should be greater than T of hold, where theta is, we have considered the combinational part delay, and T hold is hold time of flip flop 2. So let's introduce more practical scenario in this equation. So what actually happens, it when clock edge appears here, it doesn't suddenly appear at this CK pin. It takes some time to reach the CK pin, and that is the latency. And suppose the latency for the flip flop 1 is L1, then after L1 this edge will arrive at this point, and after that arrival of this edge, it will launch the data, right? Similarly for flip flop 2, if flip flop 2 is having latency of L2, then after L2 time this edge will arrive at this CK pin of the flip flop 2, right? So L2 is the latency of flip flop 2. And what we have seen in the setup analysis, that this data is launched by this clock will be captured by the next rising edge. That means this edge of clock, right? That was the setup analysis. In hold analysis, what we make sure that this data launched by this edge of clock should not be reached too fast that the previous captured data is be overwritten on this flip flop. So what we have told here, previous captured data, and previous captured data has been captured by this clock edge, not this clock edge. This clock edge is going to capture the data launched by this edge only. So previous data is captured by this clock edge, and we make sure that this captured data should not be overwritten, and it could happen if this path is too fast, means this data is arrived before the hold time of this flip flop, right? So previously captured data should not be overwritten. So that's why we check the hold analysis on the same edge of clock, not the next edge. Okay, so hold analysis we need to do on the same edge of clock on which the data is launched, right? So let's introduce L1 and L2 in our equation. So instead of this much of time of the data arrival at the deep pin, it will include the L1 latency, which takes the clock to come from the clock pin to the CK pin of this flip flop 1, and T hold is also added, and L2 will be added on the T hold side, right? Where L1 is the latency of flip flop 1 and L2 is the latency of flip flop 2. Let's add one more practical scenario, that is the hold uncertainty of this clock. So what actually want here? We want that the right hand side, that is this clock should arrive early and this data should arrive late in order to meet the hold equations. So if it arrives due to some issue, if it varies, its arrival time varies and it becomes early, then there is no problem. But if it becomes late, it is problematic, and hold and uncertainty at this edge. So we need to consider uncertainty of this edge, later uncertainty. So if it comes previous this edge appear, then there is no problem, but if it appears later, then we have to take care of that uncertainty, that is the hold uncertainty. So we have to add this hold uncertainty on the right hand side. If you remember, in the setup uncertainty we have taken care of the early arrival and we have subtracted from the right hand side. Here we need to add that much of uncertainty in order to take care of the clock uncertainty. So final equation would be clock to Q delay plus combinational delay plus the latency of the flip-flop 1 should be greater than hold time plus latency of clock flip-flop 2 plus hold uncertainty of the clock, right? And THU here we have THU indicates hold uncertainty. So in left hand side our data arrival time and right hand side our data required time, and opposite to the previous setup analysis, our data arrival time here should be greater than the data required time, and the difference between the data arrival time and the data required time is called here slack. Opposite to the setup analysis, in setup analysis what we have seen that data required time minus data arrival time is slack. Here data arrival time actually it should be greater, that's why data arrival time minus data required time is slack, and our negative slack means hold time violations. Now simplify this equation. So we know that L2 minus L1 is the clock skew between these two flops. So let's replace let's subtract the L2 minus L1 here by taking the L1 to the right hand side. It becomes L2 minus L1, and replace L2 minus L1 with the T skew. So our final equation will be clock to Q delay plus T combinational delay should be greater than hold time of flip flop 2 plus skew clock skew plus hold uncertainty. Okay, so we have seen here that the setup analysis is done by default on the next edge of arriving clock, that is one clock period, but hold analysis is performed on the same clock edge, right? That's the important thing. Here I have an insight. Many times we have heard that hold timing check is independent of the clock frequency, and same we have derived here. You can see there is no appearance of T clock here, that is the clock period. So we can say that it is independent of clock period hold analysis. But my question is here, is the above statement always correct? You need to think on this, and if you understand you can comment on the comment section. Okay, so next let's see an example of hold timing. So suppose we have combinational delay of 200 ps here, and clock to Q delay, that is this much of delay is 40 ps, and each buffers have delay, clock buffers have delay 50 ps 20 ps sorry, and hold uncertainty of the clock is 50 ps, and hold timing of this flip flop is 140 ps. Suppose this equation is this much data is we have. So let's analyze the hold timing analysis. So as per our equation we have derived in the previous session, previous slide, we can put all these values. So TCQ is given here 40 ps, T combo is 200 ps, and L1 is given L1 is the delay of two clock buffers. Obviously we are ignoring the interconnect delay here. For 40 ps L1 should be greater than the hold timing of this flip flop is given here 140 ps. So 140 plus 120 is the L2, because 1 2 3 4 5 6 buffers is there. So 6 into 120, that is 120 ps plus hold uncertainty is the 60 ps. So if we add on the both sides, then arrival time will come at 280 ps, and required arrival time is 320 ps. So if we subtract the required arrival time on the arrival time, it gives minus 40 ps of flag. So minus 40 ps means negative sign here indicates the hold violations. So let's see the way of fixing the hold violation. So again, we will consider the data path, and in data path, in our equation, data path delay is appearing on the left hand side, and left hand side should be greater than the right hand side. So definitely we need to make this path that means we need to we can do the VT swapping in this path, and from lower VT cells to higher VT cells, so that we can increase the delay in this path. Similarly, we have seen this is the clock common clock point, and before this point we have no effect in this path, and in path 3 we can if we increase the delay of this path, it comes in the left hand side, and increasing this path will help to meet the hold timing. So we can increase this path delay, this clock path delay, and similarly in segment 4 in this much of path we can and this is coming on the right hand side, so we can decrease the delay. So opposite to the setup analysis, we can do the launch flop, late clocking, and we can do the capture flop, early clocking, in order to meet the hold timing analysis. But again, we need to analyze the previous paths and the later path. Then we can only do path 3 and path 4 optimization, right? So our preference should be first in the data path only. If it is not being fixed using the data paths, VT swapping and other techniques are also there, and then only move to the clock path. Now let's discuss a sub case where both the flip flops are negative edge triggered. This case is quite similar to the previous case, only the difference is that the type of the flip flops are negative here, negative edge triggered. So you can see here this dot indicates the negative edge triggered flip flops. So instead of rising edge, data will be launched by the falling edge. That is the only difference in this case. So data will be launched by this edge, the falling edge, and captured by the next falling edge. So setup analysis will be done between these two edges, and hold analysis will be done between these two edges, right? So setup analysis equation is not going to change as we have previously discussed, and similarly the hold analysis equation is going to be same as previously discussed. Only thing is that data will be launched and captured on the negative edge of clock. That's the simple case. So again, I have a question here. Is it possible to occur setup and hold violation on the same path having same starts and end points? I would like to see your answer in the comment section. And in next session, we are going to discuss where both launch and capture elements are flops, but opposite nature of the flops, that one is being launched by the positive edge clock and captured by the negative edge clock, and vice versa. That could be interesting because there is a half cycle path concept is there. We will see that in the next session. Okay, so thank you for watching this session. If you find interesting this video and useful, please like this video and subscribe our channel, and share this video with your colleagues and friends. So you can now reach us and connect us in this Facebook page of Team VLSI, and also you can read the blogs. We have started the blogs on teamvlsi.com, and you can join us on Telegram also by searching Team VLSI on the Telegram. Thank you for watching.